Hello. In this video, I'm going to illustrate how to use the chain rule or implicit differentiation to solve problems involving related rates. When we say related rates problem, the idea here is to compute the rate of change of one quantity in terms of the rate of change of another quantity. The procedure involves finding an equation that relates the two quantities and then use the chain rule to differentiate both sides with respect to time. Before we illustrate this by examples, following are some important strategies that we can adapt in solving problems involving related rates. These are actually general principles. The first one is, of course, read the problem carefully. It involves understanding the problem. Okay. Second, we draw a diagram if possible, because the diagram will help you arrive to a solution to the problem. Third, you introduce notation. You assign symbols to all quantities that are functions of time. Fourth, you express the given information and the required rate in terms of derivatives. Fifth, you write an equation that relates the various quantities of the problem. And whenever necessary, you use the geometry of the situation to eliminate one of the variables by substitution. You can use the chain rule to differentiate both sides of the equation with respect to t, and after that, substitute the given information into the resulting equation and solve for the unknown rate. Okay, let's start with our first problem. Suppose that a brain tumor is spherical in shape. If when the radius of the tumor is 0.5 centimeters, the radius is increasing at the rate of 0.001 centimeter per day. What is the rate of increase of the volume of the tumor at the time? Okay, let's analyze the problem very carefully, and we must be able to identify the given information from the problem. What are the quantities mentioned in the problem? And after that, we'll try to describe the relationship of those quantities so we can form an equation. First, it says here when the radius of the tumor is 0.5 centimeters. Let us use R for the radius, okay? So we have the first given, which is radius for R equals 0.5 centimeter. Then we have here the radius is increasing at the rate of 0.001 centimeter per day. Now, whenever you see the phrase increasing at the rate of or changing at the rate of or decreasing at the rate of, it means that you have a quantity that changes with respect to another quantity. Like in this case, the radius is changing with respect to time. You can see the unit of measure here, centimeter per day. This shows that the radius is changing with respect to time. Okay, and this is also this actually the derivative. This describes the derivative of the radius with respect to time. Right. So therefore, we can denote this by so we have here the given Okay, r equals 0.5 centimeters. Then the second given here is described by this phrase here. No? So when you say radius is increasing at the rate of 0.001 centimeter per day, it means that the radius is changing uh, per unit time, okay, or is increasing per unit time, okay. And this is actually denoted by the derivative of the radius with respect to time. So we denote that by dr dt, okay, which is equal to 0.001 centimeter per day. Then the question is, what is the rate of increase of the volume of the tumor at that time? Again, we have a phrase, rate of increase. This is again referring to the change of one quantity with respect to another quantity. That another quantity, of course, is the time, right? So when it says rate of increase of the volume of the tumor, we were talking about the change of the volume with respect to time. So this is also similar to the derivative of the volume with respect to time, or we denote that by dV. So this is the quantity required, okay? Now, notice that it is mentioned here that the brain tumor is spherical in shape. So we have a geometric figure. This is actually a familiar geometric figure, no? And if you remember from your geometry class, uh, since we're talking about the volume, the formula for the volume, if you remember, that is given by 4 over 3 pi r cubed, right? And this formula actually describes the relationship between V and R. Okay, now since V and R are functions of time, to be able to find for this notation dv dt, we're going to apply the chain rule for this, no? Meaning compute for the derivative of this with respect to time, both sides of the equation. So we have this, right? The derivative of the volume with respect to time, and the derivative of 4 over 3 pi r cubed with respect to time. And applying the chain rule or the implicit differentiation, derivative with respect to time of v is, of course, dv dt, while here you have 4 over 3 pi is constant, so can write this outside of the operator. Then you are left with the derivative of r cubed, no, with respect to time. Applying the chain rule, this is 3r squared, right, times the derivative of r, which is dr dt. Then you see here the t and 3 will cancel, right? Okay, so we're left with dv dt equals 4 pi r squared dr dt. Again, take note that we are looking for dv dt, the rate of increase of the volume of the tumor at the time when the radius is 0.5 centimeters. And the quantities are r and dr dt. And we can see that they are the given quantities. So we can simply plug this into the formula. So we have dv dt equals 4 pi, your r, which is 0.5, okay, centimeter quantity squared, and then your dr dt, which is 0.001 centimeter per day. Then simplifying, this will become 0.25 centimeter squared. Multiplying that with 4, you will obtain 1 centimeter squared. Now, if you have centimeter squared, this can be cancelled with the centimeter, not cancelled, but multiplied. So that will become centimeter cubed. That's why your dv dt becomes 0.001 pi, okay, centimeter cube, cubic centimeter per day. What is the implication of this? The implication is your rate of increase, okay? The rate of increase of the volume of the tumor is 0.0015 cubic centimeter per day. Okay, so that's for our first example.